the second colloquium of the semester, but it's the first colloquium of the aula inaugural. So it's been promoted from a colloquium to an aula inaugural, which means that it's also the time that we give the certificates for the Young Physicist Prize. So every year we have a competition together with the Journeys exam where the top 5 scorers get prizes. So this year, not all the 5 are here, but I'll read off the winners. So starting with 5th place. So for the people who don't know, it's an exam that we give every year in which there are, I think, 5 questions about different topics from undergraduate physics, but they're hard questions. So it's a 3-hour exam, 3.5-hour exam, and the scorers usually do very well with their career. So, okay, so in 5th place in this exam from last year is Mateus Baliza Paulikiewicz, who's aluno from USP São Paulo. He got, so the top score is 100 points. He got 37 out of 100 points, so you can see it's a hard exam. So he'll get 200 reais. Right now he's at Perimeter, so he's not here because, I don't know exactly, did he already start the program at Perimeter?
He's finishing. He's starting a PhD in August, yeah.
Okay. Okay, so in 4th place is Santiago Ferreira, who's aluno from Bariloche, from Instituto Balseiro in Bariloche. So he got 41.5 points out of 100 points. So he'll get 400 reais. Okay. He's not here, he's in Argentina. Well, no. Well, he's going to be here. So he's actually in his 3rd year of undergraduate. So he's going to come again for the this year. So he didn't go to Perimeter yet because he's still has 1 more year. So we'll give him the money when he comes this year. In 3rd place is Gianna Cruz Pestana. So she's from USP São Paulo. She got 42.5 out of 100 points, and she's here now. So she's doing her master's degree here. So maybe you can stay down here and then we'll take a picture. So in 2nd place is Renan Gomes de Albuquerque from Universidade Federal do Paraíba. He got 48 out of 100 points, so he came in 2nd place. He'll get 800 reais. So he's doing his master's degree here also. And then in 1st place is Vicente Viati Figueira. He's a student from USP São Paulo. He got 51 out of 100 points. I think he's somewhere in Europe now, but I don't know exactly where.
I don't know.
So we offered him a master's degree here, but I think he got an offer somewhere in Europe. Okay, so let's thank the winners. So I'll take a picture. Okay, very good. So now we'll go to the...
I introduce, yeah. Okay, so let's introduce our speaker. So our speaker today is Raul Abramo from USP. So as usual, let's introduce a little bit his career. So he got his PhD in physics in 1997 in Brown University. Then he has been a postdoctoral fellow at University of Florida and LMU in Munich, but he was also a visiting fellow at Princeton University and University of Pennsylvania. Then he became a professor in USP. And he is a cosmologist, and he worked in many different subtopics of cosmology, including inflation, cosmological perturbation, phenomenological and observational aspects of cosmology and astrophysics. And recently is mostly working, from what I understand, in the structure formation, galaxy evolution, quasars, dark matter, dark energy, and things like that. And the talk today, the title is A Robust Cosmic Standard Rulers from the Cross Correlations of Galaxies and Dark Sirens.
Thanks, Dario. Thanks, everybody. Thanks for the invitation. And very glad to be here in this first lecture, to see also the students that got the prizes. I noticed that a couple of them, I taught them myself also a few things, so I'm glad to see that I didn't destroy their careers in any way. So they learned physics despite some of my lectures and classes and interactions, so congratulations for
And
for
they
the
also
prize
did well
winners.
your exam, because they passed it. They
Sorry?
win. The prize was for the exam that you contributed to write.
Right, so,
So they did well
yeah.
your exam
On
as
top
well.
of that, yes. So there are two barriers there to be overcome. So, yeah, so this talk is about the main problem in cosmology. Actually, cosmology started with this problem and is still coming back to this. It's coming full circle. And it all comes down to the fact that measuring distances in the universe is really, really, really hard. Things are very far away. It's very hard to see them. There's no way that you can get anything to go there and back. So how do you measure distances actually in the universe? That's a key question. That's something we still struggle to do. There are many techniques, but they are all dependent on some assumptions or something. There's always some technical details that make things harder than you would think. So starting from Hubble, down to this day, we've been struggling with this. And for a long time, this wasn't a big deal because we knew so little about it. Sometimes you're not concerned of something because your error bar is so large that everything goes inside. You don't really care. Oh, it's all in there somehow. But as technology improves, as our techniques get better, the error bar starts to decrease, and then you have a struggle you have this competition between precision and accuracy. And right now, what we have is that we have two very accurate predictions for the way in which the universe expands, but they are very far apart. And this is in the context of this talk today. I'll tell you about a new way of measuring distances in the universe. So that's cosmography. So cosmic standard ruler is about measuring distances. And this is done by combining galaxies and dark sirens. So let me ask you, the new students here, does anybody know what a dark siren is? No, not only the new students, nobody. All right, so a dark siren is, first of all, dark. Let's start with that, right? So you don't really see it. It's invisible in some way, but of course, if I'm using it, I must detect it in some way. So these are mergers of compact objects, typically two black holes that merge, and we don't see them with light, so they are dark. However, we detect signals from that merger through gravitational waves. So I'm talking here about combining gravitational wave observations with galaxies, with observations of galaxies in the universe, and using that to measure distance. So this is work that was done. Do I have a pointer here? Or I can use my mouse here. It doesn't matter. Anyway, so it's work done with these people here, one of whom is Ricardo, who is here somewhere, collaborator who started to teach me about gravitational waves, but the project was mostly carried out by the students here, which are João, Ian, Isabella, who was a postdoc here and now is in England. And this is a paper that appeared late last year and has now basically been accepted for publication in JCAP. So let me start there with the basics motivation here. Why the hell are we going back to Hubble's problem? And the reason is the following, is that we have a problem with that now, that there are two main ways of measuring this. So this is the Hubble parameter in some units. The units are kilometers per second per megaparsec. A megaparsec is like 3.2 million light years. So that's kind of the centimeter of cosmology. We measure things in megaparsecs. So that's our life. Megaparsec is the typical separation distance between galaxies, maybe even too small for it. Galaxies are typically separated by a few or many megaparsecs. So if you want to measure distances in cosmology, you have to measure many, 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 hundreds, thousands of megaparsecs. You have to go that far. Now, we want to measure something which is here, and in the horizontal axis here, you have all the ways in which people have been trying to measure that expansion rate. Expansion rate is a relationship between the distance and the velocity with which things are moving away from us because of the expansion of the universe. So it's a measure of the expansion rate of the universe. And these are many different ways, right? But if you just look very, schematically here, there's one of them which is not being shown here, which is the first one here, which is a measurement that depends on well, which is basically, sorry, it's over here. The first one is this box, which is over here. It's hard to see from where I'm standing here. So is this box there, which is basically the same type of measurement that Hubble was doing 90 years ago, right? And these measurements, they come, and they usually are telling you that that thing you're trying to measure is over here, 73, 74, something like this, with uncertainties that are becoming smaller and smaller. So that's the way in which Hubble would measure this. That's the way that we use something called standard candles. So these are Cepheid variable stars. These are supernovas typically, okay? So that they give you this value here, right? So this is not really a plot. It's just a list, okay? Now, there's another measurement here, which is this measurement here. Just look at the first point and maybe the other ones over here, but basically these points over there, which are the points that you, where you are using the cosmic microwave background. So that's the first light of the universe, when the universe was very young and decoupled matter from radiation. And this is an extremely precise measurement that we do with a satellite called Planck. And when we do that measurement, we get something which is much smaller. It's over here. It's about 67 or so, with also a very small error bar. So these should be two measurements of the same thing, the expansion rate of the universe. They should agree if we are using the right science, the right model to predict or to describe things, but they are not. So here you also see many other ways of measuring that distance, but they are more complicated. They depend on very precise, very, let's say, finicky, complex modeling of whatever it is that you're trying to measure. So I'm not going to talk a lot about this here, but basically, these are the two measurements, and they disagree. They disagree to something which we call now 5 sigma. So it's a tiny chance that it's just a statistical fluke. It's not a statistical fluctuation. It seems to be there. So there is a problem with this, right? Either these measurements are wrong, and it's very hard right now to see how they could be wrong. We even have now data from the satellites like JWST that seem to confirm that. It's also unthinkable that these measurements here that were done with the cosmic microwave backgrounds, they were wrong intrinsically. However, what we have to remember is that these measurements here, which are the blue box here, are what we measure using objects which are nearby. So stars which are near to us and supernovas. So typically these are galaxies which are not too far away from us. So we use the speed and the speed and the distances to those galaxies which are nearby. Whereas this measurement here is a distant measurement. We actually measure something at a very high redshift or large distance, and then we just basically we extend that measurement down to today using our best cosmological model. So when we say that the cosmic microwave background predicts that value for the Hubble expansion rate today, we actually mean that we make a measurement here, and then we extrapolate all the way down to 0. So there's some model dependence here. So there are plenty of potential systematic errors with this measurement. There is model dependence and also, who knows, systematic problems here with this measurement as well. But the fact is that they don't agree to 5 sigma. So that's the context here of the work that I'm going to try to talk to you about. Okay? Okay, so given that we have the situation, how can we improve on that? So one of the main things that has been happening and that you should watch out for the next few years is that it's not like we only see the universe through distant galaxies anymore. It's not a simple picture of, look for galaxies and you map out the universe. The universe goes much deeper than that. We can now see the universe in many different types of objects, not only galaxies, but also quasars, in hydrogen. We also now, and this is critical, have started to see the universe through the eyes of a gravitational wave detector. This will improve dramatically over the next few years, not only because the existing detectors like LIGO, Virgo, and Cagra, they have become better with time. People learned how to extract more from them, but also because we have new detectors being dreamed up and that will be constructed, like the Einstein telescope and others, that will make observations which are really amazing if you think about it. We can expect now to see the gravitational wave signals in a few years from these detectors going all the way to redshifts of 10, maybe even 20, who knows. That's almost all the way in distance back to the same place where the cosmic microwave background came from. So we're talking about coming on this scale here of things all the way down to here with gravitational wave detectors. And what's more, we see them in the whole sky, because gravitational waves don't care if you have a galaxy, if you have our galaxy in the middle of the way. They just pass through it like it was nothing. So that's the main thing that we have to watch out, and will be really amazing if we could use that for doing our science. So now it starts to get a bit more technical, but it's not too, don't worry too much, because this is something that everybody here saw in electromagnetism, okay? So basically, you remember that you can expand your field or your electric potentials or whatever in multiples. And that's the way that we can describe the universe as well, because we see things through our past light cone. That's all the information we can ever get. And when we are describing the universe on large scales, to very long distances over the whole sky, we need to use that language. And this is what I'm going to introduce to you. So basically, what we have is a measure of how the matter is distributed in the universe. The simplest way you could think of is that these are points here, and then you just have to know what the distances they have between each other. So this is how we map out the universe. We map the galaxies. Doesn't matter that a galaxy is here, or there, or there, or there, but it matters if the galaxies are closer by or more distance apart. So we measure this correlation between galaxies, which is a key component of our description of the universe, in terms of something called a correlation function, okay? This correlation function can be in many different ways. You can put your data in real space or in Fourier space, or even you can make a spherical harmonic decomposition. It doesn't matter, but you come always back to the same place. It's a two-point correlation function. And what we are doing right now is that we have so many galaxies and so many objects in the universe to all redshifts that we can really map the universe as if they were onion shells, right? So we have all these onion shells that describe the way that the universe is at each point, at each radius from us. And the larger the radius, the more distant in the past is that shell, right? This is a shell at early times. This is a shell at later times. This is a shell right next to us, for instance, right? Which is basically the present. So that's how we need to, that's the mathematics that we need to basically harness in order to get some information out of this, right? So here's a picture, the picture that you have to do. Yeah. Right, so maybe this picture makes it easier, right? So this is instead of being our real universe, which is a 3+1, 3 dimensions of space and 1 dimension of time, and it's not easy to make the light cone in 4 dimensions. Here is a 2+1 picture of that. So we are here. So this is us right now, right here, right? And this is our past light cone. And these sheets here are time equals constant hypersurfaces. So, of course, you have to move them to 3 dimensions to see everything, but here is a good picture. So we look back in time, and we see, in this case here, would be just a ring corresponding to each instant in time. Of course, in real life, will be a shell. And as you move more far away, we see more in the past. And then this is the description that we have. This is the inherent description that we get. This is how we ought to describe the universe. We can make other approximations sometimes, but this is how the universe presents itself to us. So this is basically how we want to describe cosmology also, right? So I'm just going to spend a few words, but not too much, because this is not a technical talk. So I'm just going to say that this is what we do here, all right? So we describe the universe in this way, and then we take our information in that sense, okay? This is some mathematics that I'm going to skip here, okay? So sorry about that. I should just have eliminated these slides, but this is basically the measurement that we do. We count the galaxies in each shell here, and we make the correlations of those shells. And this is something that we call the angular power spectrum. So that's the let's say, the ultimate description of matter distribution in our universe. Okay, so these are these angular Pau spectra. So basically, so let me just go back. Maybe I ought to say something because I already. So basically, each one of these shells you decompose in spherical harmonics, the same ones that you know from electromagnetism. You find the spherical harmonic coefficients here, basically, okay? And then you correlate those coefficients, and that is your angular Pau spectrum. And that's the observable that we have. So that's the simplest way of describing the matter distribution on all shells that you have, that you can see the universe, okay? All right, so that's a bit technical, but that's not critical if you didn't understand too much, don't worry. Okay, so let me go through this because this doesn't matter. Now, let's go down to the really important, interesting stuff here. Gravitational waves. So gravitational waves allow us another view of where matter sits in the universe. True, when we see a gravitational wave, that means that you have a binary pair of typically 5, 10, 15, 3, 2, something like this, solar mass objects that merge, and they emit a signal that is then captured in one of our gravitational wave detectors. And on the basis of that signal here, so this is time here, basically, and this is like the way in which those arms of those detectors wiggle around. So we detect that, and on the basis of that, we see which polarization we are seeing on each one of those arms. Then we use those polarizations there, together with a function here that we can basically model analytically, right? And then what we want from this, what I want from this, myself, I'm not so much interested in the mass of that system there, or the angle of that orbit of that pair with respect to our line of sight, which is this I, right? What I really want from this is the distance. So that's the key thing from the gravitational wave detection that we can do here with any gravitational wave detector, is that the signal that you see in your detector goes like 1 over the distance. So we can directly infer from the basis of our observations, knowing these formulas here, how to get that distance. So we use the waveform, you do some math, and you arrive at the distance. Notice that this is impossible for a galaxy. There's no such relation for a galaxy because you just have no idea what's all the rest of this for a galaxy. There's no modeling. There's nothing. So we know that the light from a galaxy goes like 1 over distance, or if you want, the flux goes like 1 over distance square. But you don't know what's multiplying that 1 over distance square. There's no modeling for this, and there will never be, because a galaxy is a collection of billions of stars. There's no way ever that we can model exactly what is the luminosity of a star, of a galaxy. Even a star sometimes is hard. So this is the only object for which we can, through an observation which is relatively simple, simple, where's Ricardo? Ricardo's like, there's nothing simple about this. Well, about a detection like this, you get a distance directly. The flip side of this is that when we do that, when we see a signal like that, what we cannot infer is the redshift, so how fast it is receding from us, because that information turns out to be completely mixed up with the mass of the object. The mass actually becomes a frequency. You can think about it like you think about Kepler, right? Have something moving over here. If it's more massive at the same distance, that means that it moves faster. So the frequency, so mass becomes frequency. Now, because of the redshift, frequency gets dilated, this time dilation, exactly like you learn in relativity, right? So there's no way that we can infer redshift independently of mass in these measurements here, so there's no redshift. So for black holes, for black hole binaries, we don't see redshift, we only see distance. Okay, so there are many ways of trying to get then, let's say, a distance to redshift relation. So that's basically, I should have started with that. What is the Hubble relation here? Is a relation between distance and redshift. Redshift, which is, of course, proportional to velocity with which something is moving away from us. And this turns out to be something like this, and this, basically this, the incline of that curve is what we call the expansion rate, right? So we need, in order to make the Hubble relation, in order to draw this, we need to know both this and that. Now, for galaxies, knowing Z is extremely easy because you just use redshift. Light gets redshifted, so whatever atomic line here gets redshifted to there. For galaxies, this is almost impossible to measure. You have to infer in some very indirect way. For black holes, it's the opposite. You know this easily, but you don't know that. So it's like you have something which you're measuring, which is all over here, and you have other things which are totally unrelated, which are over there, but you don't know which is which here, and you cannot draw that relation. Yeah, you infer that, so in this case it would be h minus 1, but that's basically the idea, right? So we can combine black holes and galaxies to try a measurement like this. Yes, there are many ways. You can start with something which is not even a dark siren, which is a neutron-star merger. A neutron-star merger is definitely different from a dark siren because it actually emits light. Everybody here must remember in 2017 when we had that famous kilonova, which is the only neutron-star merger ever recorded so far, and we actually detected where it came from. So in that case, we could both make one measurement of the distance here, and we had a very good measurement of the redshift. So we had one point where we can draw this line here, right? Okay? So we found where it sits, the galaxy, we measure the distance through there. So basically we do something which is kind of what I'm showing there. Distance to redshift, so that point there is basically is a measurement like this. It turns out the uncertainty in the distance is very large because we cannot see really both polarizations of that gravitational wave from different angles. Deconstructing the distance from the observation with the few detectors that we have is kind of a bit uncertain. So that one object has a kind of a uncertain distance. But on the basis of that, people were able to, in 2017, draw a completely independent measurement of H0, which has this probability distribution over here. So it doesn't resolve really that tension between the cosmic microwave background measurements of the expansion rate and the local measurements with supernovas, which are over here, the supernovas, over here for the cosmic microwave background. So you see that it's kind of the probability that the true value is somewhere over here. You see it doesn't really resolve anything, but it's promising because it's a single measurement, right? Who knows, in the future we have more. So this is one case of combining distances and redshift and getting a measurement. But in this case, we actually get the redshift because we could see exactly where it was coming from. It's important to notice here that not only for the kilonova, for instance, not only we don't know the distance very well, we didn't know the position in the sky. So this is how we could localize in the sky the event of the kilonova. And LIGO, the gravitational wave detector, could only see, well, it's coming kind of from over here. You see this region here has, I don't know how many hundreds of square degrees, but I think I remember something like 600 or maybe 1,000 square degrees. So it's a huge area in the sky. You don't know. Well, you could say that kilonova, based on the gravitational wave observation, was coming from around here, where around here is, like, look at the sky, the whole field of view that you see with your eye is kind of the size of this region. So it's a kind of big region, right? So right now, for each individual measurement, the errors in the position of that object are very large. Well, you can go one step further and say, okay, we have many, many more mergers of black holes than you have on neutron stars. Right now, what's the number? We have about 200 black hole mergers against one neutron star, roughly. That's the number that we have. And it's probably going to be this. I mean, models vary a bit, but probably more than 99.5% of the events will be black hole mergers. So people said, okay, so let's say that we now make a probabilistic approach where we look at some region where we know that the gravitational wave source came from, and then we stack all the galaxies in that region, and then we try to see what is the likelihood that that gravitational wave signal was coming from one of the galaxies in that region. So that's a very complicated matter. It can be done. It's a probabilistic approach that depends on many priors about the populations of black holes and so on. So you can combine them together, and what you get is something like what you see over here right now. You can get a little bit better than this, but it's very uncertain also, right? Okay. So we can measure distances with black holes, but it's very hard right now. What is the future looking like? Well, the future is looking like we are actually kind of over here. So this plot is old. So it's 2 years, right? The slippage in this plot, 2.5 years. So we are now actually kind of over here in the middle of run 04, right? Or the end, towards the end. So yes, so okay, so we are kind of over here in this plot here. So 03, 04, 05, these are the different upgrades to the gravitational wave detectors that exist already, right? However, so they are getting better. You see that they are covering more distances. They are going deeper into the universe. However, what we have right now is that since we know that gravitational waves definitely exist, I mean, for a while there, as you know, even Einstein doubted the actual existence of gravitational waves, but we now know that they definitely exist. So people have planned new facilities, new observatories to detect gravitational waves. One of them is this thing called the Einstein telescope. This is one of the, let's say, incarnations of the plans to do Einstein telescope, which is basically a much more powerful version of the LIGO, which is not only longer arms, better detectors, but also underground because of the main sources of noise for these gravitational detectors, which are surface waves of the Earth and waves in the sea and things which are basically on the surface of the Earth. If you go down, if you go underground, you know, 50, 100 meters, then that source of noise goes down dramatically and you can observe much more. So there are plans now to build two big facilities for gravitational wave detection. That's the Einstein telescope and the Cosmic Explorer. The Einstein telescope will be in Europe, and Ricardo here is the lead of the Brazilian Einstein telescope group, and we are interested in doing something with that. And also in the United States, there is talk of producing something called Cosmic Explorer, which will be this huge 40-kilometer arm gravitational wave detector, which can, you know, go, both of them will be able to go to redshifts of 5, 10 to literally many billions of light years away from us. Okay, so now for the rest of my talk here, let's see how much I have, which is the actual work that we did here. All right. So now let's think about this problem of distances in cosmology, but from the perspective of somebody that cares about, somebody like me, that wasn't initially interested so much in the expansion rate of the universe. For me, when I started being interested in mapping out the matter in the universe, I just thought that the expansion rate issue in cosmology was going to be solved by now. I never thought that this was going to be a problem. Let's think about where galaxies end up in the universe. And let's think about where black holes end up in the universe, right? And let's think about how they are related, the places where they end up. So consider that let's say that you make a map, a redshift survey, so a map of galaxies where you don't know the distance, but you map all the galaxies' positions in the sky, the angular positions, and the redshifts. Okay? So that's one galaxy map. Or many, whatever, right? So let's say you have one survey to rule them all of galaxies here. So we know things are more far away because of the redshift, but we don't know the distances. Now, on the other hand, now and in the future, we have more and more maps of binary black hole mergers that we detect through LIGO and in the future Einstein telescope and so on. Now, for those we don't know the redshift, and we don't know, sorry, for those here, we don't know the redshift. We know the distance, but not the redshift. So these are complementary. Now, what turns out is that all of them, they are sitting on the same cosmic structures. And there is one thing we know about cosmic structures is that the universe that we see today is built on a pattern of these structures, which is a very particular pattern, where if you look nearby a galaxy, it's very likely that you'll find another galaxy, but if you look far away, it's less likely. So that's a very tight and very highly increasing correlation function. So these things are related in some way. The question is, how exactly can you combine them to measure how you can correlate these things together? So here, I don't think it's showing very well, but the galaxies are behind there, so I guess everybody is imagining that, right? So basically, there's a way of combining them together that takes into account that underlying matter distribution such that you can then correspond D to Z on each place there. So that's what we did here, a systematic way of doing that, a recipe, if you will, for making that measurement. And basically, you can think about this in the following way. Let's say that you put one map on top of the other, but you have the wrong recipe for connecting distances and redshifts. In this case, the distances are systematically larger than what they should be. Well, in that case, if you try to correlate the black holes with the galaxies, you will have a weak correlation. Same thing if you make a mistake the other way around, if you assume that your distances are too small compared to the true distances, then the correlations are also a bit smaller. However, if you get it right, then what you'll see is that the black holes are more highly correlated with the galaxies. Because after all, if you think about this, binary black holes, where do you expect them to be? Well, they will be overwhelmingly in galaxies anyway. So that's basically the game that we have here, and we basically told people how this could be made. So that's the key picture here, now that I'm showing. So basically, we have the maps of black holes here in distance, and a map of galaxies in redshift. And this plot here is all the correlations that you can draw between galaxies at a redshift Z and black hole binary mergers or Dyke sirens at distances D. So this is one scale. So this here is that scale here in blue. This here is that scale in black. And these are all the correlations that you can do between all the galaxies and all the black holes in those shells. Okay? And what you see here is, first of all, well, let's go for the easy one. So if you correlate galaxies with themselves, so galaxy of redshift Z1 with another galaxy of redshift Z2, and you make the average of this for all the galaxies. Of course, you will have a high correlation when they coincide. Because like I told you, the universe is built on a structure, a web of structures which are highly correlated. So you see a high correlation here. Now, if you get a galaxy at a redshift of 0.5, and you try to correlate with galaxies at a redshift of 0.3, which are very distant, then you just take two random galaxies anywhere. And these correlations are nothing better than a random one. So you have basically zero in the end. Okay? So is that okay? Right? You see also from the shape of that function that the correlation function just drops very quickly when you move away this way or that way. So that tells you that the correlations are high when you are nearby, and they are weak if you are far away. Now, the same thing would be for black holes. However, there are so few black holes that correlating a black hole with another black hole is like correlating two almost very rare things with another very rare thing. The signal is very small. So you don't see it here, but it's there, okay? So that line continues over here, but it's very weak, very small signal, okay? Now, look what's happening over here. This is when you correlate galaxies in a redshift Z with distances D. Okay, so this is D and this is Z if you want. So this is Z here and D. So that's the cross correlation of galaxies at a redshift Z with binary black holes at distance D. By the way, I drew this figure wrong here. I drew this way, it should be this way, okay? Just never remember. So it actually should be actually like this, okay? So forget about this, okay? I never know which one is that way. I have to think too much in a talk, I can't remember. So this is the cross correlations of galaxies and black holes in all possible distances and in all possible redshifts. And what you see here emerging directly from that correlation measurement is dl of z. So you directly retrieve the redshift distance relationship, or the Hubble relation. So basically that's it. That's nothing more than it. Our paper was just using this and just doing the math and doing the simulations and inferring, doing the statistical inference at the end, and seeing what you can get from present, future observations of black holes. Okay? Yes? No, this is a simulation here. Thanks for the question. Current data, we are working on current data right now, but current data analysis is like maddeningly complicated. We made a proof of concept with simulations, so this is what you expect. This is a simulation for what you expect in about 10 years or 15 years from the Einstein telescope, together with LIGO, basically.
Sorry, I also have a question. The challenge was in thinking this correlation or in doing the analysis after the...
Well...
Or both?
The idea of combining galaxies with black holes is not new. Okay. People thought about this maybe even 30 years ago. It's how you do it. Nobody knew how to actually do this. People were trying, but in ways that are inherently absurd or completely dominated by model dependent in some way. This is basically model independent. There's nothing that we do here. There is modeling, of course, in the waveform of the black holes, but again, a binary black hole, let's say I'll go out on a limb here in front of people that know better, but you know, what is the simplest object in general relativity is a black hole. What is the second simplest object in general relativity? Two black holes. So that's it. It's like the hydrogen atom of general relativity. Of course, black holes are not that simple because they can have angular momentum and spin and so on, but to first approximation, that's the idea. Okay? All right, so that's it. So the rest, so basically what we did is that let's forget about this because that's what cosmologists have been doing for the past 40 years. And about the, so let's focus here on that cross-correlation between galaxies, and then let's see how much information we can actually get here about the cosmic distance scales. So that's our paper. So that's basically it. So that relationship here for, let's say, a simple cosmological model, which is called the lambda cold dark matter model, is this one. It's basically that integral. So that thing here has basically two parameters. If you want, right? So that's H0 and how much matter or how much dark energy you have in the form of a cosmological constant, but you can change that if you want, and you can make other, but that's just how we would model something like this, but if you want to measure that curve here, if you want to measure those points there, not the curves here, but those points, you don't need that formula, just to be clear, huh? What you want to find is, you want to map that out, you want to map this out with the observations, and then, of course, you can test whatever theory you want. Why does it work? Why does it work so well? Well, if you look at the correlation function, the two-point correlation function of galaxies, or pretty much any type of cosmic object, right? That function is very highly peaked at small distances. So the closer you get together, so if you fix a galaxy here, and you ask, on average, how many galaxies are around a radius of 10 megaparsecs or 1 megaparsec, as you get closer to the galaxy, the correlation increases a lot. So it's much more likely to find galaxies which are nearby another galaxy than if you are far away. And that's what's happening here. This function is very very steep. So if you move away from here, from the place where the black hole and the galaxies are basically in the same structure, that correlation drops down that way, or if you want, that way and that way. And that's why the signal is focused. Of course, the signal is washed out a little bit by our uncertainties, of course, but the theoretical uncertainties here are not relevant. It doesn't matter if this function here is this way, or if it's that way, or if it's this way, that plot here will change very little. That is one of the key aspects that make this method really, really good. So basically, that's what I was telling you here. The correlations drop if you move far away from a point. So you can fix the black hole and vary the galaxies, or you can fix the galaxy, vary the black hole. If you want to think about this, doesn't matter. Anyway, so these are some caveats here. So this is the reason why it works. Let me skip over this because it's just the same thing that I already told you. So how did we prove that this worked? Okay, we didn't want to make just a calculation, which is, to some extent, people have done calculations before without ever pointing out exactly how you make the measurement. So we wanted to make a simulation here that was kind of a more convincing proof of concept. So let me go over a few lines and why we think that we have our method is well justified in claiming to be a robust measurement of distances. So first of all, we create a simulation of our entire past light cone using the typical distribution of matter that we already know exists both from the cosmic microwave background and from galaxy surveys. And we basically simulate the whole universe in this way. It's a very simple simulation. Of course, if you want to simulate the whole universe, you cannot go in detail, right? So this is a typical galaxy distribution in this simulation here using this code called GLASS. So GLASS basically gives you all of those onion shells from here down to, I don't know, 10 billion years away. I don't know, 10 billion light years away. Well, that takes care of the galaxy side of things. Now, we have to now think, well, where would I put black holes in here? Because that's something we actually don't know. We don't know where the binary black holes appear, and we don't know which types of galaxies are the more likely hosts of binary black holes. And we don't know what's the ultimate number of black holes, what they will be, but that's the point when you have to go over to the people that do the gravitational wave observations and ask, okay, so what is your scenario for what have you learned from LIGO up to now? What are you forecasting for LIGO in the next few years? What are you forecasting for the next generation detection? So that's one of the key areas where Ricardo and Isabella, Miguel, and so on came, because they knew how to do that sampling. So they knew how to come and say, okay, give me a galaxy somewhere at a certain redshift. What is the likelihood that a black hole will appear in that galaxy? So we have simulations that do that as well. So we start with the galaxy map, and then in each galaxy here, there's a tiny probability that a black hole merger will appear in there, a dark siren. We do that. We end up with a few of those events here. That's our map of dark sirens. Now, that map here, have to be careful because some events have high mass. They are very well localized, both in angle and in distance. But some of them are poorly localized. Let's say you have a low mass in the threshold of your observations. So you have a big angular and radial angle. So what you see here is basically the probability cloud of each one of those events. And you see that they are kind of spread over. If you want to do a zoom in here, you would see something like this. So that's the cloud of objects here for each one of those black holes, for each one of those dark sirens. Just to be sure, here in the galaxy side, there is no error. The redshift is known with extreme precision, and the angular position is known almost perfectly. But for black holes, we have a big uncertainty here, both in the angular position and in the radial position. So those are key ingredients of this simulation. So To my knowledge, this was the first time that anybody attempted to do a realistic simulation of black holes, a distribution of black holes in a cosmological volume for these kinds of applications. So, yeah. Yes, I'm coming to this. Good question. In a few slides, if not the next one, I don't recall, I'll talk exactly about this. Yes, it's over here. So, let's look on Earth here, right? I don't know how to draw this here, but so here is LIGO in Washington, here is LIGO in, so let me draw, this is a poor rendition of the, of the Americas, right? I don't know, something like this, right? This is a Gulf of what? Europe here, Africa, whatever. So this is here, and then you have another detector in here, which is really not doing a lot, and the one in Japan, which is not working so far. So, of course, if you have a detector which is a microson interferometer, and something comes the wrong way, you don't really measure anything, right? So the sensitivity distribution on the sky, if you average out over the year, right, turns out to be something like this. For LVK run 5, so that's LIGO Virgo Cagra run 5, this is basically how well you would see your black holes, how many events you have, and how many events you have is also a manifestation of the accuracy of those, of each individual measurements, which is over here. So the galaxy map is over there, so of course the cross correlation is something in between. So no, it's not homogeneous in the sky, and we take into account that, right? If something comes in a bad angle, it will be basically uncertain everywhere. No, it can. Yes, it can. I mean, sometimes you don't know if it's coming from here or there, right? It can be bimodal. Yes, but not with that number of detectors. Yeah. Yeah. With just LIGO, I think it can be bimodal. With LIGO Virgo Cagra, then that breaks that degeneracy. So here is basically the error in the angular position and the distance for right now, for what's going to happen in maybe a couple of years, right, with LIGO. And this is what's going to happen with the Einstein telescope in Cosmic Explorer, or the Einstein telescope with the existing ones. You'll have a huge number of objects counted now, with, of course, all kinds of errors here, but the number of objects with better measurements will increase dramatically, especially in the distance. Angular position will not improve so much, but the radial position will. Okay? So that's what the future is looking at. Now, for the final thing here is that, okay, I put all of these simulations in, I turn my statistical inference machine on. What do I get at the end by using this kind of test? This technique called peak sirens. So let's here. This is a forecast of what LIGO could be able to do in 3-4 years, LVK, right? So end of run 5, it's 4 years from now. This is the kind of thing we expect. So if you're measuring 2 of those parameters in the distance redshift relation, so that's the value of the expansion rate and the amount of matter, right? So these are always something that 2 things that you measure together. Actually, you measure even more of that together. You would see here an error bar of about, 7-8% here. If you are only measuring the expansion rate, you would see something like 4% error here. That's what we are forecasting for this. What is the situation right now? Right now, we are seeing something that you combine everything, including the neutron star measurement, which is by far the most constraining one, and you get about 6% precision. So this is competitive with what we have right now. And what is happening in the future? So now we are talking about construction of the Einstein telescope. When it's going to start, maybe 2030, 2032, depends on how much support it has, but we're talking here at least 10 years. So these are of the order of 50,000 dark sirens up to redshift of 2 and maybe even more far away. And here we are talking about a measurement of H0 which is at 1% or below. So that's more than enough to break the Hubble tension and to tell us if the true value, you see that our simulation value for H0 is in between. It's neither the low one or the high one, we put it in here, but with 1% measurement, or even with 2% or 3%, we could already start making a determination of that value here. Again, this is a completely independent measurement, and as opposed to the low redshift measurement of the expansion rate that depends on calibration of stars and supernovas, which is intrinsically complicated and prone to systematics, and as opposed to the measurement of the cosmic microwave background, which is model dependent, this has very little room for the same kinds of systematic errors here. Let me skip over this. Let me also skip over that because this is not too important. So these are, so this is an interesting detail here that maybe it's worth mentioning. Gravitational lensing. We know that when you see a source of light behind a massive object, that light can be deflected by that object. You sometimes can even magnify that source or demagnify. So this effect also happens for the measurements of the signal from black holes. They suffer the same thing because these are signals that travel in the same pathways that light do in the universe, right? So we computed the effect of gravitational lensing on these measurements. And there were some indications before that it could be an important effect. We proved that it's something that you can marginally detect, but it doesn't affect these distance measurements here. So that's, let's say, a byproduct of our analysis here. Okay, so let me go towards the end because I think I'm extinguishing my time. So this method here is a robust method to make a direct measurement of the distance scale without assuming anything about the cosmological model, without assuming anything about calibration of stars of any type. So this is cosmography. So we use dark sirens which have no electromagnetic counterparts. So we don't need something like kilonovas where we both see the gravitational wave signal and the light signal at the same event. In this case, we can use the vast majority of objects that will be detected by the gravitational wave detectors. This can be a test not only for, let's say, low universe physics like the expansion rate right now, but this is basically the only way in which we can do cosmography up to redshift of 10 if we want. If we see anything to those redshifts, and we will see, we already see, for instance, quasars and active galactic nuclei to redshift of 9, 10, and we will see the universe in radio, for instance, up to those redshifts. So we can do cosmography, so distances in the universe, up to redshifts of 10, maybe even higher. We will observe within 4 years, we will be able to make a 4% constraint on H0 using this technique, and a 1% constraint in about 10 years or so. We have many things to do, so we are working here with Ricardo, with former students, with Isabella, also Bernardo, which is here, is involved in this project, and many more people. So there's lots of things to do, and I wouldn't claim that this method is completely systematic free. This is something that we sometimes like to dream, but it doesn't really work like that in the real world. So there are many ways in which we are testing this. One of the key things that we are doing right now, which is very involved and complicated, is applying this to real data. So what we have right now already available is the data from LVK up to run 3. So that's about 100 and how many events? 90 events. So over the whole sky. It's a challenge. We are tackling that. So basically, Isabella Matos is basically heading this up together with our colleagues from Portsmouth in England. So there's much to be done here, but that's basically what I want to say. Okay, thank you.
Okay, we have already questions.
Yes, Thiago.
Hi, Raul. First, thanks for the talk. I have one very quick question, one which is a bit more tricky. The quick question is, wasn't there supposed to also be a telescope that was an interferometer? And what happened to that? You didn't mention anything like that. And
We do have telescopes which are interferometers, but in radio, not in optical, because in optical will be a bit difficult.
Okay. The other thing is so assume that you solve the tension one way or the other. That means that the indirect and the direct methods are actually measuring different things. What would you say is actually happening?
Okay, so let's go that way, right? Because it's, of course, that's what we... So let's say both of them are correct. That would be the dreamland, right? Because then there's something wrong with the model. Like I said, the CMB, cosmic microwave background, constraint on H0 is model dependent. And that's why you have many papers claiming that this or that, or this early dark energy model, or this dark matter, dark radiation model, or whatever, solves the Hubble tension. That's because they introduce something that changes that relation between the high redshift measurement from the CMB and the low redshift inference of H0, right? So if that was true, if that was a new ingredient, that would be in itself amazing, because that new ingredient, by the way, is not dark matter, it's not dark energy, it's something else. That would be amazing, right? It could also be that you come on top of exactly, let's say that you make this measurement and it comes exactly on top of the CMB one. Then you would tell the people that are doing Cepheids and supernovas for 90 years that they got something extremely, dramatically, catastrophically wrong, and they have to look down on their data and they have to look again, right? I mean, you can go on and on. I mean, I don't know what's going to happen, but any one of those things would be a lot of fun to watch, even if I'm already retired and I'm watching from the sidelines, drinking beer.
So, hey.
Hey,
here.
yeah, hi.
So you said you don't need kilonovas to calibrate.
No, that doesn't rely at all on kilonovas.
Okay,
Kilonovas, you can say that are like completely separate from this.
Yeah, no, that's my question. But let's say you have data on kilonova. You expect them to fit in some way, or it's completely independent?
Oh, the kilonova should be
in your curve.
Should be in the same category. I mean, it also doesn't have almost basically no systematic, right? So yeah.
And the one experimental point you have on kilonova fits in your curve.
Yeah, no.
Okay.
Of course
And then if you have more, you expect them to...
the problem is always the distance measurement, right? So for 1 kilonova, that distance measurement has an error of like 15%, which is still a lot. And it's possible that you can get more kilonovas with a bit better accuracies, but we don't know first how many we have. It could be that that one was a statistical fluke, that you wait for another 10 years and maybe 1 or 2 come by. It could be that you have many more, or it could be that you get one just in the right place, that you get the measurement of distance really well. But kilonovas are in the same category of the dark siren. The modeling is exactly the same. Actually, for kilonovas, it's a bit more difficult because these are neutron stars, and the neutron stars have internal structure. I'm not entirely sure if you can, but I don't think it plays a really big role.
My question is that
there's no systematics in the same way that we don't have, so they would break the degeneracies in the same way.
Okay, so the question is right that. I mean, if eventually they appear and they offer a good sign, it could validate your approach, or...
Sure, they are complementary, right? They would, but they would be, let's say that, let's think here. Let's say that gravity is not general relativity and the distance is something else that we are missing. Then they would both be wrong in the same way, because the distance measurement for the kilonova is done in exactly the same way that we make the distance measurement for the dark siren.
Okay.
Hi, George.
So my question is very simple. Basically, if I understood correctly, the game, in an ideal world, what you would like to have is enough resolution in the gravitational waves in such a way you could pinpoint exactly the galaxy that would host the system and extract the redshift from this, right?
Exactly, which is what you get from the kilonova, because it emits light.
Okay.
But if you can get a precise localization with gravitational waves, that will be equivalent.
Okay. But the problem is that the resolution that you have from gravitational waves is not so good.
Yeah.
Okay. So just to have a feeling of the size of your challenge, thinking of the Einstein telescope and thinking of a typical binary fusion that happens 1 billion light years from here, okay? So how many putative galaxies, what's the order of putative of possible galaxies that could host this, this binary system that you're inserting on?
Oh, it's a huge number, but that's not the point.
This huge number is
but that's
1,000,
no,
a
no, no, but
million,
that's
or
not
what?
the point. The point is that you are making a correlation between millions of objects. It doesn't matter which one exactly it is.
No, no, no. I understand that you are overcoming this problem.
Okay.
I see.
Sorry.
But just to see the size of your problem, right?
The size of the data, not of the problem.
The size of the problem is you are not able to pinpoint precisely the galaxy because you have a lot of uncertainties. So what would be the number of galaxies that could host this binary? So what's the order? 1 million, 1 billion, or what?
So that's a hard question to answer because you can have galaxies which are tiny and big. Let me answer this in the context of the simulations that we did, which are trying to mimic basically the galaxy surface on the one hand and the number of black holes that we expect to see based on the best models that people are using for these new detectors, right? So what we have is of the order, so let's take a look here. For instance, for LVK plus Einstein telescope, we are talking about of the order of 20,000, 30,000 black hole events up to Redshift 2, whereas the number of galaxies is about 20 or 30 million. So we are talking about one object per every 1,000 galaxies, if so, right? If perhaps even less, right? The point is that when you correlate all the black holes with all the galaxies and all the distances, you are overcoming the low counts of the black hole measurements with the high counts of the galaxies, and overcoming the uncertainty in the angular and radial position of the black holes with the very precise position of the galaxies. We are not limited by the number of galaxies, actually. The number of galaxies you can double or make half of it. The signal won't change at all, actually. So it doesn't really matter if you use more galaxies or less galaxies. Actually, it doesn't matter that the actual galaxy where that dark siren came from, whether or not it's in the catalog. Something that I didn't mention here, that I thought it wasn't important, but now I think it is that when we make this map here, of the black holes, means that we get a galaxy here that somehow, okay, you get a black hole merger here. So that's this guy there, right? When we do that, we take that galaxy out from our galaxy sample. So it's not even there. We take it away. It's irrelevant that that particular galaxy is in the data set because that's not the point. You are correlating the black hole with the cosmic structure. It doesn't matter that the actual host of that black hole is there. It matters that the black hole is immersed in the same structures as the galaxies are. This is the point. So the statistical question is a bit more easy than what it sounds like, because it's not a question of the actual coincidence of individual objects. That's completely beside the point. It's a measure of statistical correlation, which it doesn't matter.
Okay, thank you.
Of course, it is very sensitive to the counts of black holes because they are so few, but the galaxies, no. You can double, make half of them, will be the same.
More questions?
I missed the point. What is the reason of that you use these dark sirens and not every black hole binary event?
No, that is every black hole binary event.
You?
Of all the gravitational wave observations, all but one are dark sirens. Everything else which is one is a neutron star merger. So every single observation which is not a neutron star merger, a kilonova, is a dark siren. We are using them all.
In your data, in your analysis?
Yeah, of course.
I thought that by the what you said in the beginning, you were interested particularly.
No.
Sorry.
These are dark sirens are black hole mergers, and every single one of the observations we made so far are of dark sirens. The only one which is not is the kilonova of 2017. And we don't know what the future will be, but we know for sure that there are many, many more dark sirens, black hole mergers. Dark sirens equal black hole mergers, okay? By the way, on LIGO, I think there is one possible neutron star black hole merger, right? Two. One without counterpart? And two mixed. So, right, so we are talking about 4 then. 4 events out of the 90-something, right? But the other ones, the neutron star and black hole for all purposes are also dark because we don't really see anything coming from them. Even neutron star mergers can be dark because, you know, if they happen in a place where you can't really pinpoint where they came from, you never see the actual light from that explosion, you don't know where it comes from, it becomes a dark siren. So, to all effects, every single one, except the kilonova 2017, are dark sirens. Even neutron star mergers, if you don't see the optical counterpart.
More questions? Okay, if not, we can thank
Thank
Raul
you.
again.
Thanks, everyone.